inviting me here. I am very much honored. It's my first time in Korea, and actually some of you already know my husband is actually Korean, but somehow we have never managed to visit Korea before, so it's my first time. I'm very happy to be here. It definitely feels we are sibling countries. So, okay, so I have promised Professor Sut that today it will be a very elementary introduction to Schubert calculus. It is a beautiful subject. This is my personal opinion. It's a very beautiful subject, and in fact, the basic ideas, in fact, it is possible to discuss in a very concrete way. Of course, in the later lectures, I hope to show you some more techniques that are perhaps you could say more advanced, so to say. But today I really want to be very concrete, very elementary. It's just simple linear algebra and so on. So I hope you will forgive me, and some of you I think are already expert in some of this, so I apologize, but it is nice to see everything together anyway. So, okay. So before I do anything else, I would like to just place Schubert calculus into context, if you like. How can one think about it? How does it relate to other areas that maybe you are already interested in? So, and as I was thinking about how to say that, there were two different ways I could say it, and I think they are both useful, so I say both of them. Okay, so again, of course, I should say as a caveat that you are getting a very personal view on Schubert calculus, but anyway, there are two ways to think about Schubert-type problems. So it is a very large area, and so people who say they work on Schubert calculus, they might mean very many different things, but anyway, probably most of us agree that it looks something like this. At least this is as I say. So one way is to say, okay, well, Schubert calculus, well, it somehow sits inside enumerative geometry. So what do I mean by that? I will give more examples in just one moment, but before I do that, let me just try to say some general words. So this is about counting some kind of geometric objects of a given type that satisfy some given set of geometric conditions. Of course, that's very vague. I give you more specific examples momentarily. So, of course, that's very vague. It's too vague. Okay, so examples coming. Okay, and then that, the way that it is usually presented these days, that should sit inside the very large and active area, of course, of algebraic geometry more generally. So that is one way to think about what is Schubert calculus. However, I must confess, I am not trained as an algebraic geometer, and I came to Schubert calculus from a very different route, from equivariant topology and symplectic geometry, in fact. And so, and that's not just accidental. In fact, there are many equivariant topological or symplectic viewpoints, in particular the Morse theory of a moment map, which lends nice ways to think about Schubert calculus, or lends some tools for doing Schubert calculus. And so, although this is one classical way of thinking about what it is, I want to give you one more little advertisement or a diagram for how to think about it. So it turns out it's not just algebraic geometry. If you are an equivariant algebraic topologist or an equivariant symplectic geometer, and or also lends insight and tools to the area. And my training is in symplectic geometry. So I personally like to think of it like this. So this is, again, a personal view, but I like to think of this diagram. And of course, it's somehow an area in which, so you have geometry of various types, algebraic, symplectic, topological, etc. And then you have algebra, so you might think algebraic geometry or somehow symmetric polynomials. And then there's combinatorics, Young diagrams, and so on, Bruchau order on the permutation group. So, of course, this is even more vague in some ways, but it's just advertisement. Oops, geometry. So I just like to think of this triangle. Somehow it is an area where these all lend a hand and come together. So, I'm sorry, so here I should say a little bit more specifically. So here I said at least some general words about what enumerative geometry should be. Here I should say some words about what I mean when I write that. So when I write this, what I mean is, so I forgot to write the words equivariant here, but I guess I wrote it here, so I can be forgiven. Okay, so here what I mean is equivariant. So it is, in fact, people are interested in both the ordinary and the equivariant versions, but anyway, so I will put it in parentheses. So I mean intersection theory meant in a very broad sense on particular varieties. So on five varieties. So G mod P's. So G mod P, so G is a Kac-Moody elite group and P is a parabolic. Okay, and of course the classical example is the Grassmannian, and then you might want to think about the Borel, which is the five variety instead. The full. But also I want to add one more comment, which maybe I do it here. So in fact, classically is what people, or classically, whatever, most people these days, the modern Schubert calculus is about what I just wrote in yellow. But over the course of the next few days, what I want to say is actually, really it would be more interesting if you added something else in pink and various subvarieties. Thereof. So it's not just any old subvariety of the five varieties that I mean. I will have to tell you more specifically over the next week or so what I want, which particular subvarieties of the five varieties deserve to have a Schubert calculus. But that is for next week. But anyway, this is what I mean when I write that in this diagram. Okay, so that was just context. Okay, so now let us try to begin a few more things, concretely. Okay, so I'd like to begin by, so I'm not an expert, in fact, in enumerative geometry, but let me just try to give a flavor of what kind of questions, at least historically, these were about. So let me begin there. So I will answer the question merely by giving examples. Okay. So I think I have question 0 and 1, 2, and 3. So here we go. So enumerative geometry asks certain kinds of questions about how you count some number of things. So here's an example. So this is from a long time ago. I think it's about this, and maybe other people in the audience know better. Anyway, here's the question, yeah? How many circles? We're just talking about, yeah, plane geometry, high school geometry, yeah? How many circles are tangent So that's the geometric condition, yeah? Okay, the tangent to 3 given circles in the plane. Okay, so you just imagine, okay, so here are 3 given circles in a plane, okay? And you just start trying to draw circles which are tangent to all 3. Okay, and generically the answer is supposed to be 8. There's supposed to be one sort of inside, you can imagine it right there, there's sort of one inside, and then there are 3 which contain exactly one of these circles each, then there's 3 more that contain exactly 2 of these circles each, and then there's 1 more that contains all 3. So generically it's 8. Of course you can also imagine examples where it's not possible, but yeah, but generically the answer is supposed to be 8. So this is one example. So answer is generically 8. And I should say, I didn't know this before, but I, of course, searched on Wikipedia. And there's beautiful figures, actually. So if you enjoy things like this, then please see. I don't know who did that article, but they really took time to make some beautiful figures. Anyway. Anyway, so this is a historical, very historical, as you see, example. Okay, so this is, but in more modern times. So for questions 1 through 3, I'm going to talk about Schubert for Schubert calculus. So this is Herbert Schubert, not Frank, the musician. Okay, so here we go. So by the way, again for his history, he was born 1848 and died 1911. So relatively modern, but still a century ago. Yeah. Okay. All right. So I can just give you 3 examples of the kinds of questions that he asked and answered systematically. Yeah. So for example, again, let's just stick to plane geometry. Sorry. I'm doing R3 now. So how many lines intersect 2 given lines and a point in R3. Oops, sorry, wait a second. Yeah, R2. Okay, so that one, again, generically 1. Okay, but I'm also giving these examples to motivate one thing, and I'm going to do that with the next question, which is a lot easier than this one, but it will allow me to motivate the thing that I want to present, and perhaps for this audience I don't need to motivate it, but let's do the question anyway. So what is the number of points of intersection of 2 lines in R2? Well, that's easy. 1, generically, except the reason I write up such an elementary example is just to say, yes, but it could be parallel, right? In which case it would be 0 in R2, but of course we all in this room know that really you should also count that as 1 because it's the point at infinity. So that's going to allow me to rephrase some of these questions, and in particular question number 3, in terms of projective geometry instead of plane geometry. So that's the reason I'm introducing, speaking about this. So let's write down the answer and what we will do next. So again, it's generically 1. But, as we all know, the lines may be parallel. But of course, we all know that should mean that it's actually, we talk about the point at infinity as the intersection. So the lines may be parallel. In this case, what we ought to be doing to count the point at infinity. Okay. Okay. So I've been talking about plane geometry here, but now what I want to do is to just quickly remind you, okay, so what we'll do is introduce a space in which all the points of infinity exist. Are actually points in the space, yeah? So just a quick reminder and also just to set notation. So affine n space will be, so I'll denote that A naught to A1, where the AI are in, so either the reals or the complexes. And then the projective n space, I'll denote it Pn, and as is customary, I'll write it in homogeneous coordinates. And of course, the equivalence relation is that non-zero scalar multiples are equivalent. Yeah, so of course these are, so the interpretation is there's lines in an plus 1. Okay, very good. And then the point about the point at infinity is, as again, P1, so over R is of course R union infinity. So I've just actually tossed in that point. Yeah? Okay, very good. Now similarly to this example, where I've just closed off the real line to add that point at infinity, similarly, I will want to talk about the following correspondence, and that's going to be for question 3, which is the one I'll discuss in detail for the rest of today. So that's this.
You know, there are two small black holes.
Yes, I noticed, but I was afraid of what would happen if I tried to use them.
It's a very difficult mathematical question. I mean, in which order you should write
Yes,
this proof?
absolutely.
So that maximize it. I've been always trying to do, but I couldn't find the solution.
Well, so
Where you start at the word how to. So that's a very.
So I entered the classroom and I looked at the situation and I decided I cannot solve this problem in front of 20 other people. So okay. So similarly, I hope you will agree with me. Yeah, that. And this is the correspondence I will use for the rest of the time. Is that a line? So please recall. Oh, I'm so sorry. Oh, okay. Never mind. Okay, let me just write this first. Okay, so a line in A3. So here, when I say line, I mean it's a line that doesn't necessarily go through the origin. So you could say it's an affine line. Okay, these are in one-to-one correspondence with planes in A4 that do go through the origin. And planes in A4, two-dimensional spaces in A4 has a name. It's the Grassmannian of two planes in A or C4, and so I'll give that a name. So this is by definition the Grassmannian 2,4, Grassmannian of the space of two planes in R4, A4, whatever, C4, R4, whatever we're doing.
So A3 or P?
Here I think I'm doing lines in A3, right? Yeah, A3, right? Yeah. Yeah, I'm just saying I haven't said anything about projective space, I'm just going to bump myself up, right? Yeah. Yeah, okay, great. Okay, so my point here is that so if I were to give an enumerative question of the type question 1 or question 2 in A3 about lines in A3, then in fact what I ought to be thinking about is planes in A4, and that puts me in a projective variety, Grassmannian, two planes in R4. Okay, so question 3, which is the one I'll discuss in detail for the rest of today.
How do you associate this line
So if I give you a line, okay, so if it's hard to draw. Okay, so the point is, if I have a line in A3, no, wait, I'm sorry.
Planes are easier.
Sorry, I guess the plane is easier. I should think about the plane in A4, and I should intersect it with the hyperplane, the affine hyperplane where the last coordinate is equal to 1. Yeah. It's just the usual thing of how you build coordinates for a projective space, yeah? Okay, so the one I'll discuss in detail for the rest of today. It's somehow everybody's first example in Schubert calculus. It's how many lines intersect 4 given lines in A3. Okay, and Schubert's answer way back when is generically 2, pardon me. Okay, and what I would like to do today is to show you how to think about that using so-called, shall I say, modern methods, just using cohomology. Okay, and combinatorics and other fun things. Okay, all right. Okay, so as I just said, so the rest of today, the goal of today is to give a modern answer, modern, how can I say, derivation of the answer using cohomology, Young diagrams, etc. Okay, so that's what we'd like to do. This is somehow everybody's first example because it's the first example where you can really play with all the ingredients. So, okay, very good. So that was the introductory, pep talk. So, here we go. So to do this right here, I'll have to do a little preparation for how we're going to think about and work with the Grassmannian of 2 planes in R4. Oh, I'm sorry. So I should have said, so this, let's see, this board, that board, and this half of that board was supposed to be my motivation, my introduction to the idea that when we think about this question in the first place, we should actually think about it in here and not in here. Okay, so that's why I just said, okay, so we need some various methods to think about this Grassmannian. Okay, so that is what I'll do first. Okay. All right. Okay, so let's do some elementary things. Okay, so here we go. So, well, let's see. By linear algebra, I'm looking at 2 planes in our A4, so I need 2 vectors that span that plane. Let's write them down in terms of some standard coordinates. So let's just do it. Okay, so a 2 plane in A4 is determined by a basis, of course. All right, so again, just to be very concrete, okay, so I will think of these PIs as row vectors, and I'll just put them in a 2x4 matrix. Yeah, so again, please forgive me, let's just write it out. Oops, I'm sorry, P10, P11, P12, P13. So I'm just labeling the coordinates as 0, x0, x1, x2, x3. So this is just the 0th coordinate, 1st coordinate, 2nd coordinate, etc. Okay, and then of course the second one. so, and of course I've chosen some standard basis once and for all with respect to which to write coordinates. Okay, very good. So that specifies the two-plane. Of course, it's not unique, but I never said it was. Okay, so specifying the plane. Okay, but anyway, at least we can work with a matrix. Very good. Okay, so as I just said, it's not unique. Changing the basis doesn't change the two-plane. Okay, so we're going to do basic linear algebra. Let's put this in reduced row echelon form in a particular way that's amenable to what I say later. Okay, so it's not just, so it's a particular choice. So, by doing Gaussian elimination, okay, we can put, maybe I give it this a name. In a certain row reduced echelon form. Okay, and once I do this standardization, so I put it in row reduced echelon form, then the matrix will be unique. Okay, which is unique. Yeah, so once we agree that you will always put anything in a certain form, then it is unique. And because I'm doing such a small example, 2, 4, there are in fact six ways that the reduced row echelon form may look. So I will actually write them out. Okay? So in our case, in our GR24 case, there are 6 possibilities.
You choose, let's say, 2 vectors.
Yes.
Suppose you choose different vectors, and you do row echelon form. Reduce the row echelon form is just the 1, and.
I will write what I mean very specifically, okay. So then maybe we can agree. Okay. Yeah. Okay. Where are the pivots? Okay. So as I say, I will. Let's write this out very, very clearly, and I will have to. Let's see. All right, so, okay, I have to try to make sure this fits. Okay, so one possibility is that my reduced row echelon form will end up looking like this. Okay, so the stars are just free variables, free parameters. And so this is, of course, the most generic situation, yeah, where both rows have something non-zero. Here, so I can make this the rightmost 2 by 2 matrix into the identity. Okay, okay, so if I can do that, then I always do it. Okay, and then I have this. Okay, and then, sorry, that's a parameter. This, or it could look like this. Or it could look like this. So please excuse excuse my being so explicit, but there's a reason for this. Okay. Okay, so these are the possibilities. Let me let me not circle the pivot, okay? All right, that would be, yeah. So what I claim is if you agree that whenever you want to specify a two-plane, you must do so by basis vectors that look like one of these 3, 6 categories, and there will be a unique choice. Is that?
I'm sorry, what's the
I'm sorry, I claim if I give you any two-plane in R4 or A4, and I tell you, you must pick a basis for this two-plane, where the two vectors are of this particular form, then it will be unique. Is that okay? Okay, that's what I'm claiming. Yeah? And now, the reason I wrote this out so much is because now I want to point out the connection with Young diagrams. Okay, so the way that you get 6 Young diagrams out of these 6 row-reduced echelon forms is as follows. Here's what you do. Okay, here there's nothing. I just put a 0. Here what you do is you look to the right of the pivot 1s. You look to the right where, so of course, if I have another pivot 1 over here, then this entry has to be a 0. There is no choice there, so I ignore those. But I look, where there was a parameter, and I've picked a 0 there, so I circle that. Similarly, I circle these, and here I circle this and this. Okay, here I circle this and, oh, sorry, wait. Sorry. Oh, here, yes. Okay, so these are both, they don't have a pivot here, so I circle both of these, and now I circle both of these. All 4, sorry. Okay? All right, and so what I have is some number of boxes for each choice of pivot. So let me organize these boxes like this. So here I have 2 boxes in one row. Here I have 1 box in each row, so I write it like this. Sorry, that's terrible. Let's try that again. Okay, there. And here I have 2 boxes in the first row and 1 box in the bottom. So it's 2 boxes and 1 in the bottom. And then here I have 2 and 2. Okay, so now what I can say is what we are seeing by doing this standardization is we have suddenly seen that we get, what we are seeing is, okay, so here what we are seeing is all possible. Now I will define Young diagrams right now. Okay, but what let me just tell you the result. Okay, what we are seeing is all possible Young diagrams that fit in a. Okay, so we're doing Grassmann of 2 planes in A4, so it's Young diagrams that fit in a 2 by 4 minus 2, which is of course 2 box. Okay, and in general it'll be k by n minus k. Okay, all right, very good. So of course I should tell you what a Young diagram is in case you haven't heard of that. So, brief interlude. Okay, what is a Young diagram? It's a concrete and pictorial way, which is actually very useful for combinatorialists. It's a concrete pictorial way to represent a partition of a positive integer. Okay, so definition. A partition of a positive integer n, yeah, is just a list of positive integers whose sum is n. Okay, as a sum of positive integers, lambda 1 out to lambda k, sum k, and by convention, well, okay, let me say it this way. By convention, you list them in decreasing order. So, yeah. So just to be completely concrete here. So of course, you can write, so for n is equal to 4, something like this, yeah, etc. So these are the kinds of partitions that you can get. And the Young diagrams are nothing else than you just take each of these numbers and you put them, you just list them in. So you have ones, and you have one box. If you have two, you have two boxes, and you just put them in decreasing order like this. Okay, so that's all it is. So again, so the Young diagram is obtained by the obvious pictorial representation. Okay, so again, examples here. So this one would be that, this one would be that, etc. Okay, and I have to just say that this is more than just a little trick or I don't know, picture. If you talk to a combinatorialist, then they will tell you that actually having this diagram in front of you allows you to give Young diagram theoretic proofs of combinatorial identities which are otherwise horrible and heinous, that you would have to use sort of complicated generating functions and so on. But if you have the Young diagrams in front of you, you can start arguing about moving boxes around and so on. And it actually gives you much more pleasant proofs of various identities. So it's actually, it's not just a picture, it's actually a very useful tool. But anyway, for us, I just wanted to say what it is, and again, also to say this, that what we're seeing here is somehow a combinatorial set coming out of our Grassmannian. Very good. Okay, so after that interlude, let's come back to, so end interlude, back to Grassmannian. So I was trying to advertise that I like to think about Schubert calculus as this intersection, if you like, of algebra and combinatorics and geometry. So I would be remiss if I did not at least mention the Plücker embedding, so let me do so. Okay, so another way to think about the Grassmannian is actually as a projective variety. So I take some projective space and I will cut out the Grassmannian as as a variety by a certain equation which I will actually write down for you. So here we go. Another way to think about is to embed it in P5. Okay? As the set of solutions to a very specific quadratic equation. Okay, so let me give it to you. Here's phi. It's going to give you the embedding. Here's the Grassmannian. Okay, I'm actually going to do this very explicitly, giving you actual coordinates. So here we go. So P5, I'm going to write it as Z1, sorry, Z0, pardon me, Z1, Z2 up to Z5. No, sorry, yes, P5, sorry. Okay, yes, P5, yes, okay. And here's what we do. So going back to the coordinates for the Grassmannian, which I erased earlier, so it was P1, 0, yeah, P1, 1, etc., P2, 0, P2, 1, etc. Yeah, so given such a two-plane, what I will do is take it to, okay, so I'm actually going to tell you what the coordinate z0 should be. It's the determinant, so it's a bunch of determinants, a bunch of minors. So it's the minors of all possible 2x2s. Okay, so that's why I have 6 here. The determinant of, okay, so I'll just write down 1 and then say etc. So P2, 0, P2, 1. Yeah, so the leftmost 2x2 matrix, etc. So it's the determinants to all. Well, it's just all the possible 2x2 minors. All possible 2x2 minors. Okay? Yes. Okay, very good. So that's why it's P5. Okay? Excellent. And the fact, which I will not justify, but it is a fact that the image is in fact cut out by what's called the Plücker relation. This is called the Plücker embedding, and the relation is called the Plücker relation. Yes? I'm sorry? I will spell it. I will spell it right now. I will spell it right now. Fact. So I claimed it was an embedding. All I did is write this down. But so I will just list these as facts. So it actually is an embedding. It's a fun exercise to prove it for yourself. And it's a set of solutions. It's precisely the set of solutions to the following equations. Okay, so this is called the Plücker relation. And so, of course, phi is called in fact, there are many Plücker embeddings. This is just one of them, but let's not get into that.
It's actually
Well, I can't say it properly. I say it the way all Americans say it, and I never studied German, I'm afraid. Okay, very good. Very good. So as I say, I felt I would not be doing justice if I didn't at least mention the Plücker embedding. So there is another way to think about the Grassmann N24. It's just a projective variety. Okay. But now so I've set the stage a little bit with the Grassmann, and now let's come back to this question number 3 of Schubert's that I had motivated the discussion with. So let's think about lines in A3, or instead 2 planes in A4. Okay, so 2. Let's come back to our enumerative question. What about those 4 planes? Okay, so the 4 planes in A4. Okay, so very good. So again, some notation. L1, L2, L3, L4, B, 4 planes in A4. Okay. So the notation L is because we just remember that it comes from the Schubert problem of lines in A3. Anyway, but there, so please.
Sorry, 2 subspecies or just alpha plane?
These are planes. These are honest planes. Sorry, so 2 spaces. Thank you. Yeah. So dimension 2 subspaces. So 2-dimensional subspaces.
Thanks so much.
Okay, in A4. Okay, all right. So I'll say something obvious. Okay, so 2 lines. Yeah. Intersect. So please remember. So with our oh sorry, so two lines in A3 are intersecting. That's saying that, what am I trying to say? I'm just trying to say, in our one-to-one correspondence between lines in A3 and planes in A4, one intersects if and only if the other intersects. That's all I'm trying to say. Maybe I should just say that and not try to write it down. Okay, so, so we're looking for non-trivial intersections, yeah? That's the point. Okay, so we are looking for intersection, non-trivial intersection. So, to answer our enumerative question, here's what we're looking for, yeah? We are searching for okay. Well, let's see. So how many lines intersect four given lines? We're looking for the planes in the Grassmannian, which have the property that, okay, I have these four given lines or planes. So I'm looking for the lines or planes in the Grassmannian such that each one of them intersects the given one, for all I, 1, 2, 3, 4. Yeah, that's what we're looking at. That's what we're looking for, pardon me. Okay? Now, again, at the risk of saying something obvious, I will now write that this is, okay, well, intersect from 1 to 4, those lines such that, well, that one is at least this dimension. Okay? And what I want to say now is I can describe these individually in terms of these row-reduced echelon forms, which I happen to erase, but they are in your heads and in your notes. Yeah? So each piece, each one of these guys can be described quite explicitly in terms of the row-reduced echelon forms. So I'm sorry, I'm going to abbreviate. Row-reduced echelon forms we had earlier. What do I mean by that? Well, let me be more concrete. Okay. This allows me to mention Schubert varieties. So let's do that. Okay, so what about those four planes? Well, here we are with four planes. Okay, now let's talk about Schubert varieties. That's these guys. Okay. All right, so very good. What I want to do is I want to relate, so as I just said, what I want to do is relate what we just talked about in this board and a half with what we were talking about before with the row-reduced echelon forms. So let me do that with an example. Let's take a particular L1. Just suppose that one of my L1s is a very nice plane. It's the span of the first two standard basis vectors. Okay? So I'm being very pedantic here, but what I mean is it looks like this, yeah? So, okay. Okay? All right, going back to, oh, I'm sorry. Shoot. Okay, I can't redo this on the blackboard, but if you're taking notes, let me ask you to go back and add something to your notes, if I may. So I had these 6 row-reduced echelon forms, yes? And I had the Young diagrams corresponding. And I meant to, but I forgot to write, that I will denote by C naught, C box, C double box, C and so on, the corresponding set, the corresponding subset of the Grassmannian. Am I making sense what I'm trying to say? I just forgot to introduce this notation. Yeah, so the set of planes whose row-reduced echelon form corresponds to that Young diagram, I will denote that set by C sub box, and etc. So I'm sorry about that. Okay. Okay, so going back to our C Young diagrams, going back to our C's. Okay. By the way, for those of you who know, these are just the Bruja cells, yeah? And if you don't know, let me just tell you, these are called Bruja cells. Okay, so I mean the C's are called Bruja cells, hence C. Okay, so going back to these C's, we see that, so if I'm trying to find those planes in the Grassmannian which intersects non-trivially with something with a plane that looks like this, if you go back to those row-reduced echelon forms, it's very easy to tell which ones do, yeah? It's this. So for this particular choice of L1, if I want that L to intersect with this particular choice of L1 in at least dimension 1, okay? Then I claim it's not hard at all to see that this is precisely the union of this. Well, it's all of them, in fact, except C naught. C empty set, sorry. Okay, so in fact, it's everything but C empty set. Okay? So that's why these row-reduced echelon forms, I apologize if I was boring you before, but they really are useful. They allow you to actually write down what these subvarieties are. Okay. So a couple of remarks. Okay. So when we did this, we took union of all cells C lambda. So lambda is a generic notation for a Young diagram. Please remember it's supposed to corresponding to a partition and is equal to lambda 1 plus lambda. So I will just denote that. So generic Young diagram C lambda. So we took a union over all of these C some Young diagram for those Young diagrams that contain, which is to say, if I just take off some boxes, then I will have the Young diagram I start with, so that contain the smallest Young diagram. Okay. So I'm sorry, I don't think this is the best English sentence ever. What I'm trying to say is, what do we do here? We took this smallest Young diagram, and then we took all the other Young diagrams that are appearing in our set that contain this one. And in this case, of course, it's the smallest, so I just have them all, except for, of course, the empty one. Okay, so that will come up later, okay? In fact, it will come up, so I will give it a name. So let me just give this remark a name. Okay, so for another example, okay, so this, so if the minimal one that I'm starting with is this particular Young diagram, then the union would be C these ones. Yeah, just as an example. Oh, sorry, that's a terrible English sentence. It would be the union. There we go. Okay, why am I making a fuss out of this? It's because I want to say the following. Okay, so let me make a definition. X, that's the standard notation for a Schubert variety. So now I'm making up notation as I go along, but okay, so this is by definition. So X for this Young diagram would be, by definition, it's exactly the union of all the cells that contain it. Okay? So for example, it would be this. Sorry. Okay? Similarly, etc. Okay? So, and same for any lambda following this rule. Okay? And by definition, these are the Schubert varieties. Okay? All right, fact. Okay, so these are also all varieties. Okay. So that was, oh, and of course I should say, because it's not said yet, these are the Schubert varieties. So-called Schubert varieties.
Logically, X box, X diagram
Yes.
is the closure of the
Yes.
open set of C.
Yes, that's exactly right. Not obvious, but it's true. Not at all, yes, but that is what it is. Okay. Great. Now we can solve, oh, well, we're getting there. We can solve the original question using cohomology. Okay. Okay. Okay, so, as we know, from the Grassmannian, we can think about its cohomology ring. So now, okay, so we pass to a graded ring. Very good. Okay, now, wonderful things happen. Okay. So wonderful thing number one is that these subvarieties, these Schubert varieties I mean, okay, they give rise to actual cohomology classes, yeah? And the notation here, okay, is the most obvious one, I guess you can imagine. So the X's signify the variety, and I'll use, again, this is traditional, I'll use sigma to denote the Schubert classes. The classes, sorry, in the cohomology ring. Okay, so for example, etc. Okay? All right, so these are the famous Schubert classes. Okay. Magic of cohomology number 2, which makes this business very nice. Okay, so if I take the corresponding cohomology classes, and I take the product in the ring, which is the cohomology ring, then I'll just get that number of intersection points. So the number of this intersection, the number of points in that intersection, times the top class, which in this case is the biggest box. So the reason I'm putting that there is because that's the top class. Okay? So if we can do this cohomology computation, then we've actually got our answer. Please remember, we were trying to, in fact, count points of an intersection. So that's the magic that we're about to use.
So why do I care about the Schubert classes?
I'm sorry, so I'm saying a rather general statement, but of course I will apply it to the situation where these are these are the Schubert varieties that we considered. But this is a general statement about algebraic geometry.
What do you mean by the sigma yi?
I'm sorry, so given a subvariety, its cohomology class, I'm temporarily denoting a sigma of y1.
Cohomology class.
Yeah, I'm sorry, yeah, but it's just sort of a general statement, but of course, yes, I'm going to apply it to these particular varieties.
Like it's cup product solution instead of dot product.
Sorry?
Cup product instead of dot product.
I should write, yes,
It's much better.
sorry, yes, of course,
Thanks.
of course. Thank you. Okay. And then this is another thing about cohomology which we are familiar with, but which we will now use, is so if I can just smoothly move one subvariety to another one, then its cohomology classes, their cohomology classes are the same. Yeah, so it can be moved continuously. Then their cohomology classes are the same. So in the notation as before, yeah, they would be the same. And the reason this is nice is because, of course, in our enumerative example, right, I was just given 4 given lines. Sorry, planes. I was given 4 given planes in A4, yeah? But any 2 planes in A4 I could just move by some linear transformation one to the other, yeah? So in fact, all those cohomology classes, L4, L1, L2, L3, and L4, as a cohomology class, they will give rise to the same 1. And therefore, without loss of generality, I can just use the sigma sub box that we discussed earlier. Okay, and so therefore, by this, all that I need to do is compute the 4th cup product of sigma box, and then we're done. And so I'm going to get a number times the top class, and that number gives me the answer to the enumerative question. Okay, so I'm way ahead of myself. Let me write down this. Okay, so for any plane L in A4, okay, this, oh dear me, I'm sorry, L prime. For any plane L prime, all those L's, all the planes that intersect with it, my given one, so no matter what this plane is, spanned by any 2 basis vectors of my choosing, I can certainly move it to X box. Please remember that was the one that we already said. That was the one for L prime being the particular one, which is the span of the first 2 basis vectors. So that was the special one. This is the special one. So please remember this is, maybe I'll just write it down, yeah? So please remember we had just done this. This is exactly this. So because I can just move any L prime to this particular choice of plane, just by a linear transformation, these two have the same cohomology class. So the answer to Schubert's question number 3 so with all this said, okay, so 1 through 3 implies that the answer to, okay, the projectivized version of Schubert's question number 3 is given by computing sigma naught, sigma naught, sigma naught, sigma naught 4 times. And then we will get some number here, which is our goal to compute, some number, and it should be times the top class. Oops, I'm sorry. There we go. And that number will be hopefully 2. Okay, so let's see that it is. So please remember, Schubert told us it should be 2, so that's why we're aiming for 2. We hope for 2. So let me give you the final ingredient. Okay? So now that all that is said, this is called the Pierre rule. So let me tell you what the Pierre rule is. And again, this is another justification for introducing the whole notion of Young diagrams and all these boxes, because this is a place where you will see that talking in terms of boxes really helps to actually say what the rule is to begin with. So here we go. Okay, there's a beautiful theorem/formula. That tells you how to compute this. Okay, and it's this. Let me state the theorem. You'll see what I mean about Young diagrams. So this is proven in Fulton's book, Young Tableau. So sigma, so please remember my generic notation, yeah, for one of these Young diagrams of our list. But anyway, if I want to multiply it by this smallest class, this box class, okay, then he tells you, so this is what Pierre tells you, and Fulton proves it in his blue book, Young Tableau. Okay, it's a sum over, let me write it first and then I'll explain. Okay, where the sum is over
So in this case, the box is just the minimum one?
So yes, so the
intersection of the minimum one?
I'm sorry, first of all, I meant that.
Yeah, that's okay.
Okay.
So the second one is the minimum box.
Yes, so the Pierre rule is a rule that tells you how to compute in the cohomology ring of the Grassmannian. But it's not a rule that tells you how to compute any old product. It only tells you how to compute products with this particular smallest box class. That's called the Pierre rule. But of course, thankfully, we're in that case. So that's what we'll do, okay? So, but I have to tell you what the sum is. I haven't told you what the rule is yet, yeah? So where the sum is over, okay, all Young diagrams mu that are legitimate in our problem. What I mean is it's over all mu that fit in the 2 by 4 minus 2 box. Okay, so I'm only allowed mu's that are within the discussion in the first place. So that fit in. So in our case, it's this box, but in general, it would be k by n minus k, yeah? Okay, so where the sum is over all mu that fit in this, that, I'm sorry, I'm running out of room, I'll try to write it. Okay, obtained from the particular choice I have, lambda. Okay, I apologize for this, by adding one box. Okay? So this is what I meant when I said it's a very young diagram theoretic statement even. Okay? But it's a beautiful thing. So now, so I'm almost done. So now let's just apply it and see what comes out. It's a lot of fun. Okay, so. Okay, so let's do it. So here goes. Okay, so let's do 2 first. Okay, so the Peary rule says what I should do, I should use one box and add it to that, but I'm only allowed, well, okay, in this case they'll all fit in the 2 by 2 box, so here goes. So it's this plus this. That's it. Right? Simple enough. Okay, great. Now if I want to do 3, well, that's okay, so it's the 2, which we just decided is this, times this. So now I apply Peary rule twice, right? And then we get, okay, so now, if I want, so I'll do this times that. Now, if I wanted to add a box, I could add it here or here, but I'm not allowed to add it there because that wouldn't fit in the 2 by 2 box. So for this times that, I only get this. That's the contribution from this times that by the Peary rule, and then add, and then again it's the same deal, yeah? So if I wanted to add a box here, I could add it there or I could add it there, but I'm not allowed to add it there, so in fact I just get that. Okay, and of course we all jump up and down because that's where we get our 2. But we're not quite done, so let's finish. Oh, sorry. Let me just write it out. Okay, so. Okay, one more. Oh, we all know what's going to happen, but let's write it out. Okay, now of course there's only one way to add, legitimately, fitting in the 2 by 2 box, so it's 2 times that. So the answer is 2. Well done. Okay, so we agree. Okay.
It's a generic answer.
Say again, I'm sorry?
Generic answer. Generic.
Yes. Yeah, yes, that's a generic answer.
Sigma box and box and box.
Yes. Okay. So, as I say, this is everybody's first example, but it really allows you to see everything. You see the Grassmannian, you see the Bruchhaus cells, you see the Schubert varieties, you see the Young diagrams actually doing something, and you can see the Peary rule. So this is the flavor, if you like, and well, what I will talk about over the next week is rather different, I must say, in terms of the specifics. Yeah, so I will still talk about Schubert classes, I will still talk about Schubert varieties, and I will still talk about some kind of homogeneous spaces for Lie groups. I will actually talk about the flag variety, not the Grassmannian, but those are very related things. So somehow, how can I say, the names of the characters will be very similar, but actually the inner workings will be a little bit different when I talk about it. But somehow, everything is motivated from this kind of beautiful picture where everything is interacting. So I hope to tell you about that over the week. So thank you very much.